Great, thank you very much. Unlike the previous speaker, who's been 14 years into his topic, we're actually on the other end of that, just at the concept phase. So today what I'm going to be talking about are some new device concepts that we have for a device that we're calling the Transistor-Injected Quantum Transition Laser, which combines features of the transistor laser developed here at Illinois by Professors Holonyak and Feng, with devices from Bell Labs, particularly Feist and Capasso's group, the Quantum Cascade laser, which has been very important in the mid-IR, and I'll talk a little bit about that as we go forward. I'd like to acknowledge the grad student that I have involved in this particular project, Kano Chen. She had a paper, a poster out there if anybody is interested in some further details on some of the things that we're looking at with regard to this and some of the modeling. But obviously I'd like to thank my group, entire group as well, which is still fairly small. So. With regard to the topics I'd like to cover today, I want to briefly talk about the motivation for this. Obviously in a conference like this, people understand the importance of the mid-IR, but highlighting a few of the reasons why we're interested in this wavelength range is important. I want to talk a little bit about, again, really the inspiration for this device, which was the transistor laser and QCL. And then we'll introduce the basic concept of the transistor-injected quantum transition laser and talk about what we think some of the advantages of this device are going to be. Finally, we'll talk a little bit about some of the efficiency improvement estimates that we've been working on, and then summarize. So with regard to the motivation for this, again, the mid-IR region of the spectra is an incredibly rich region for chemical transitions. And as a consequence, any mid-IR source is very useful for a number of applications: biomedical imaging, chemical sensing, chemical process gas detection, greenhouse gas monitoring. All of those applications become very important, especially for a device where effectively you can move on to a given or around a given chemical transition and dither a device wavelength around that in order to effectively look for amplitude changes, near a specific wavelength. And that's one of the things that we feel that we can do with this device, and rather than relying on device heating, which is a slow process and typical more for the quantum cascade laser, we can actually do it by a fairly rapid modulation of what ultimately is our base collector junction in our transistor. Obviously, there's military applications as well. We like to look at dual-use technologies. The mid-IR is also very important for things like defense against man-pads, surface-to-air missiles. It's potentially useful for producing atmospheric links for ground-to-air and air-to-air communication, in the, again, atmospheric passband windows. And of course, chemical detection in the IR is also important for things like explosive detection and homeland security applications. So with regard to the background of this, there's really two devices that ultimately were the inspiration for looking at this particular structure. The first device was the transistor laser, and for those of you not familiar with that, back in around the 2004 time frame, Professor Feng here at Illinois was looking at very high-speed HBT devices and also was working very closely with Professor Holonyak. What was recognized was that recombination, which is a natural part of the operation process of any sort of bipolar transistor, in a direct gap material produces light. And those photons are useful and can be used. So what they did was made a modification to a traditional HBT structure. They added a quantum well into the base region, which allowed somewhat more efficient collection of the fast recombining electron-hole pairs. The slow recombining electron-hole pairs, or slow recombining electrons, effectively get swept out in the reverse biased base collector junction of the device. And as a consequence, you have a device that can be modulated to very high speeds, and they've demonstrated for transistor lasers up to about 40 gigabits per second, relaxation, oscillation, free oscillation, with no need for external modulation. So it's a very interesting device, a device that is still early in its, I suppose, development or understanding of what can be done with it. But in and of itself is an interesting device, and something that my group is also doing some work on as well, because it could actually be an interesting functional unit for systems that require both electronic and photonic interactions. The quantum cascade laser, of course, is another very interesting device. I mean, it kind of represents the cutting edge of epitaxy, in the sense that you're producing very complex quantum structures, where you're actually getting into the mechanics of the recombination process. We're engineering the electron wave functions in this structure such that we can produce, the optimal interaction between, the quantum state in one region and the quantum state in another, by effectively varying the thicknesses of our layers. We're able to create the energy separation of those quantum transitions. And we also are working with fundamental properties such as state recombination lifetimes. By varying the quantum overlap between one state and the next, you effectively are able to obviously vary or control the time that recombination event is going to occur. So you're really unlike a semiconductor laser or a band-to-band process, where we're sort of stuck with what we have. I mean, in the sense, we can vary our quantum well thicknesses and things like this. Here, we're actually engineering the physics. We're using physics to engineer the recombination process itself. So it's a very interesting device, but it has some problems. The biggest problem with the device is that it's a two-terminal device. We have this structure that we're producing, where we're relying on quantum transitions that we've engineered into this device. But when we change the bias voltage, we're changing the field across those regions. Changing the field changes the overlap between effectively one state and the next. So we're effectively changing the fundamental characteristics of the device, the state lifetimes and the transition energies, as we change the bias on this device itself. It's an N+IN device. So from a semiconductor laser person's perspective, and some people cringe when I say this, it's a resistor laser. But still a very interesting resistor laser. So what are some of the challenges with the QCL? Again, I mentioned one of these a moment ago. Effectively, if you look at what's happening, as you climb your Li curve of the device, you're effectively changing the band bending again, which is changing both your state recombination lifetimes as well as the recombination energies. The net result of that is you have a very strong field dependence of the population inversion of the device. Effectively, there's a sweet spot where these things operate, and then outside of that sweet spot, there's a rapid deterioration of the performance of the device. Another huge problem, which was actually talked about earlier today by Katerina, is the problem of free carrier absorption. In the mid-IR portion of the spectra, you're in a range where basically using even just the simple Drude model, which begins to, you actually have more complicated processes going on in P-type material than N-type material, because obviously you've got multiple subbands present, your whole, you have heavy holes, light holes, your split off band. But in the simplistic sense, if you go back to the simple models and data from people like Spitzer and Whalen, the dependence of free carrier absorption on wavelength goes as effectively the power of the wavelength. So you have a very strong increase in free carrier absorption that occurs in the mid-IR and longer wavelength portion of the spectra. And as a consequence of that, you'd like to be able to come up with some way, if possible, to defeat that. Okay. So in thinking about those, those challenges, and again, having the advantage of simultaneously thinking about QCLs for some other projects, and also looking closely at the transistor laser work that was going on here, the idea basically was generated to utilize the transistor effect to inject the carriers into our Cascade region and to effectively stabilize the field in our Cascade region by effectively putting it in the middle of a reverse bias base collector junction. So effectively what we do is, we have a transistor or an HBT. We have a standard base junction, we have a collector junction, we have an intrinsic region that contains our quantum cascade structure. We apply a reverse bias to that structure, which basically applies the field, and we engineer the doping in both the base region and the collector region to create a depletion region around that quantum cascade region, which basically strips out the carriers that are contributing to free carrier absorption. So basically by engineering our doping levels and optimizing or doing a trade-off between our base collector voltage and the desired amount of free carrier absorption that we want to remove, we can basically generate a device that has much better power efficiencies in the end than, or much lower optical losses, and then as a consequence power efficiencies than the quantum cascade laser has. And these are basically some of the, again, the diagrams, showing, what the structure looks like for an edge emitting device. Where if you look at the figure here, we basically show the overall structure. So this is an edge-on view, again, of an edge-emitting device. We have an emitter structure, which is here. We have our base region, which is here. And obviously, as we inject a small amount of base current based upon the beta of the transistor, we then pull in a large number of electrons from the emitter contact. They flow across the base. They're collected in the reverse bias base collector junction, undergo the quantum transitions, which provide gain, and then effectively are pulled out. In this structure, although this isn't key to the concept itself, we're using some other techniques, processing techniques, to help do mode shaping, lateral oxidation of materials, which is commonly used in vertical cavity surface emitting lasers, allows us to effectively put fingers of high resistive, low refractive index material into the structure in places that we want to put it. Those fingers basically allow us both to do optical mode shaping as well as to control where we're injecting the current in the device. Again, the basic operating principle is the operating principle of a transistor, an NPN transistor. And again, this is showing the band diagram and what that looks like under your typical bias condition. So what are some of the advantages of this device? Well, there's advantages that depend upon how we choose now to bias that three-terminal structure that we now have, as opposed to effectively, the two-terminal structure of a standard QCL. The first one is wavelength tuning. So, in this particular instantiation or application, what we would do is we would have a common emitter configuration where effectively we use, one circuit to control the base current, and as a consequence, the laser power. So we have a fixed laser power or a fixed current going in. And then we would have a small dithering circuit placed on the reverse biased base collector junction to cause very small changes, right around, again, in regions where we still have a good, good overlap between, the different wave functions that, are contributing to the state lifetimes. But, again, by having a small dither, we're effectively able to produce a little minor sweep in the wavelength right around, a given part of the spectra. And that can be done very rapidly. We can also modulate this device at high speed. The N+IN QCL, which basically has a very high operating voltage, while the fundamentals would allow that to operate very rapidly, there are some practical things which cause that to be problematic. Here we can basically use a common base configuration, where once again we either fix or dither the laser wavelength, and then have a separate control which basically RF modulates or digitally modulates the emitter base junction to effectively provide amplitude modulation. So effectively this sort of configuration allows us to do amplitude modulation with one circuit or slight wavelength modulation with a second circuit. So again, it allows perhaps some interesting modulation schemes to be employed, similar to phase modulation and things that are being used in long-haul telecommunication systems. This application would largely be more like free space optical communication. So the other advantage of the device, is in the area of free carrier absorption. So how do we minimize free carrier absorption? I kind of mentioned this earlier, and this graph really helps to illustrate, how that occurs. We effectively have our Cascade region here, which we have under reverse bias. Under reverse bias, we create a depletion region around that Cascade region. We have a forward bias circuit which injects our electrons through our base region and then through our Cascade region. So effectively, by having a slightly more lightly doped p-type material, and again, we're able to reduce the doping significantly over the N+ layer that's required in the QCL. We can also play with our doping density here, but what's most important is that we create this depletion region around the structure. And if we create a depletion region around the structure, there are no free carriers to contribute to the free carrier absorption process. So we're actually able to improve the efficiency as well. So again, this is an additional advantage, beyond the rapid wavelength modulation and ability to high-speed modulate. That efficiency impact can be measured by looking at parameters like high power operation and wall plug efficiencies. There's also, again, a gain stabilization advantage related to basically, again, fixing that base collector voltage and applied field. Again, we're still in the preliminary stages, and further modeling is being done, but in some simple 1D modeling that we did, effectively looking at the mode shape overlap with the regions of the crystal that would have free carrier absorption, and also applying that across the various metrics that are important for the quantum cascade laser, threshold current densities, DQEs, total power improvement. We've come up with some estimates with regard to what we'd see just from a pure efficiency improvement of the device, ranging from something like a 25% reduction in threshold current, again, per the simplistic model that we have, all the way up to, again, with also doing some mode shaping to effectively reducing the threshold current by 2/3, improving slope efficiency by as much as a factor of 2, and wall plug efficiency by as much as a factor of 2. Again, we're still taking these simple one-dimensional models and extending them and doing full two-dimensional models and looking at the overlap of those modes, with the doped material in the structure, and in particular, the P-type material is problematic because there's not a lot of data in the literature right now on mid-IR absorption for lightly doped P-type material. So we're having to do some estimates based upon the data that is available. But again, we think that these are reasonable and what could be expected for this sort of device. So with that, we've basically introduced the concept for this device, reviewed some of the projected advantages, and then showed an estimated improvement performance for that device as well. So thank you very much.
Questions?
Really interesting. I have 2 questions. You mentioned infrared spectroscopy, and so I wondered, what do you think the tuning range would be in the relevant infrared range? And
sure.
The second question is, I didn't understand when you have the common base configuration, how the base emitter voltage or current actually amplitude modulates.
Okay, let me answer the second question first because it's easier than the first one. So basically, in that configuration, it's effectively the base emitter, the voltage that you're applying to the base emitter junction, that's controlling the amount of current that's going through your transistor. So it's a pure transistor effect. So that one is straightforward. With regard to the other, there's sort of an element of sort of it depends to that. I mean, so we can achieve limited wavelength tuning by effectively focusing on just doing a small voltage modulation in and around the particular wavelength that we're interested in at sort of a fixed temperature. So that's going to be relatively small, probably enough to span either side of an absorption peak, but not much more than that. We would have the ability to temperature tune as well. So if we wanted to look at separate peaks, we in principle could move the overall structure to a different wavelength or to a different temperature, and then again do the same dithering there. Or if we began to look, and there's a lot of work in the literature now on multi-wavelength QCL structures, where effectively you're putting different quantum transition regions in to broaden your gain spectra. If we do something like that, which is down the road, we effectively could build any structure into the reverse bias base collector junction and potentially use something, again, this is now way far out, integrate this gain structure perhaps into a silicon tuning block effectively, where effectively we do something like a Y-branch tunable laser that uses the additive vernier effect as an example to pick out different wavelength transitions with a broadly tunable laser. I mean, there's a company that's done that in the telecommunications wavelength range where they've integrated a standard 3.5 gain media with tuning arms that have been integrated into effectively a silicon photonic structure in order to realize a broader tuning range. So I know that's a long-winded answer to your question, but I think that down the road there's more functionality that we could have. In the short term, it would just be enough to maybe sense a single peak.
Let's thank our speaker. I'm sorry. We're well behind.